Most people would not write it this way, but again, the ordering and the numbering is arbitrary. So let's call this node 1, node 3, and node 2. And I'm going to call this element 1 and element 2. So what I've done here is I've swapped the names for nodes 3 and 2. In fact, obviously it's the same exact discretization. You get the same properties, but we've flipped the order. And actually, let me not do it that way. Let's call this, let's make it even more confusing. Let's call this 3, and we'll call this 1. We'll do it this way, so we get something different. Okay, so we've completely renumbered the nodes. And again, in general, we're going to have discretizations that are unstructured, and it's going to be real difficult to come up with some generalized consensus as to what is the correct node numbering. And it really isn't. It's kind of a silly statement. So the method should work for arbitrary numbering, and let's do it here. Okay, let's do this augmented approach. Again, you can do this by inspection if you see it, but if not, you might want to do this augmented approach. So let's write out the augmented matrix. Again, they're both going to be 3 by 3s. I'm just going to drop the displacement vector since you've seen that. I'm just going to directly sum them up. And this is going to give us, I should put a little more room on here. Let me zoom out just a tad bit. Okay, I think I can, well, we'll write the answer down here. So this is going to be the augmented stiffness matrix for the first element, the augmented stiffness matrix for the second element, and this is going to be the global stiffness matrix from the sum of those two. Again, they're both going to be 3 by 3s, so let's just sort of show the elements of the matrices. All right, so the first stiffness matrix connects the first element connects node 3 to node 1. So that's going to relate the forces at nodes 1 and 3 to the displacements at nodes 1 and 3. So where the zeros are going to populate are here, 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 and here. Now technically, if we look at just this is kind of a subtle thing. If I look at K11, K12, K21, K22, where this is the components of the element stiffness matrix for the first element, since the first degree of freedom is node 3, this one should technically go here. This one on the diagonal should technically go here. This one, which relates the first degree of freedom to the second degree of freedom, or the force at the first degree of freedom, which is 3, to the displacement at the second degree of freedom, which is 1. So that should go here. And then this one should go here. But you don't have to be that careful about the way those map. Because it's symmetric anyway, and you end up here with just K1 minus K1 minus K1 and then K1. Okay? But this one works out pretty easily. Now the second one relates the displacements at nodes 1 and 2. This is like U1 and U2 to the forces at nodes 1 and 2. And in this case, the degrees of freedom, the first entry would go here. So that's the K2. And then we get the minus K2, minus K2, and then the K1. All right? And so if we write this out, we just sum those together. I get up here K1 plus K2. Then I get a minus K2. And then I get a minus K1. And then I get a minus K2, and then a K1, and then a 0, and then a minus K1, a 0, and then a K1. And now if we compare those to the original stiffness matrix, let's see if I can get this right next to each other. Obviously, it has a different form, okay? But if you think about it, and I'll just mention this really quickly before I do the last example, this is really just a renumbering. So if I were to renumber this mesh so it would look like this, what would happen? And this one's a little confusing, because I would have to, let's renumber this. So in this case, what was originally 3 is going to go to 1. What was 1 in this mesh maps onto 2. And what is 2 here maps onto 3. Let me pause this. Someone's at my door. Well, I can't pause. I wish I could pause. Let me stop.